All right, welcome class. So today's lesson is using Newton's laws, 3.5, and our first focus is going to be on tension. You might remember that tension is a pulling force exerted by ropes and strings. A pulling force exerted by ropes and strings, and tension is always pulling. It's only ever pulling, and it always pulls toward the center of the rope. Now, one of the neat things about tension is that tension is the same throughout the whole rope. It doesn't matter whether you're on the one end or the other, it's the same value always. And so one way that we can say that, say the tension on one end, Ft1, we'll say is equal to the negative of Ft2. And I say negative just because if you're looking at one end, it's pulling to the left, and if you're looking at the other end, it's pulling to the right. They're pulling in opposite directions, but with the same magnitude. That might look a bit like Newton's third law, and that's because it is. It's the same. It's the action force and the reaction force. It's the same idea, and so it really just means that throughout the whole rope, all the forces are balanced. Okay. So we're going to be dealing with some tension problems here. Before we get into them, I want to say one thing, which is that sometimes we can ignore tension. Even if we have a rope and a problem or a string, sometimes we can just ignore the tension entirely. We looked at it once before. The idea is that we can combine all the objects. So if an object has a rope in it, sometimes we can pretend that two or more objects are really one combined object, and then we can ignore the tension. And that's because if the rope is doing its job, then it's pulling the objects, and everything moves together at the same acceleration, which means that the whole thing must have some net force, and you can sort of look at it all together. We'll see that on the second page. We'll do a problem that ignores tension, at least for the first half. Okay, before we do that, let's take a look at this, this question here. It says, each object below has a force of gravity of 120 newtons down, acting on it. Determine the tension in each string. So that means here we have 120 newtons. Here we have 120 newtons. Here 120, and here 120. Okay, this one won't take long. So for each of these objects, it's being pulled down by 120 newtons, and the objects aren't moving. They're all at rest. So if it has 120 newtons down, I'll draw my free body diagram here. The only thing that's pulling it up is tension, which means that it needs to be equal to 120 newtons, because the object needs to be balanced. It's not going anywhere. So that was pretty easy, I think. Now this second one, I'll draw the same guy here, 120 newtons pulling it down. Only the rope is pulling it up. You can see just the rope is pulling it up. So again, our tension is 120 newtons. Didn't change. Now, why did I show this second problem? Well, you can see in the first problem, we were pulling straight up, and I can look at the tension on this end of the string. I can also look at the tension on this end. And you can see that the tension here, it's pulling down. So our tension is pulling down on the ceiling in part A. Over here, though, it's a bit different. Our tension is pulling against the wall. But it's still the same idea. So here we have tension as well. Remember, the tension is the same throughout the whole rope, so here the wall is feeling 120 newtons of pull. And that's because our mass is pulling down on it. Okay, last problem here. We've got two objects. So I'll draw my two objects, 120 newtons, 120 newtons. Now, if you look at the picture here, we've got two masses. Both of them are pulling on the string. So one of them is pulling on the string with 120 newtons. The other one is pulling on the string with 120 newtons. So that means that in the string, there should be 240 newtons of tension, right? Well, that's not right. It's pretty common that students will say this is 240 newtons. Well, no, it's not. Let's take a look at the free body diagrams here. For my first object on the left here, the only thing that's pulling it up is tension. So that means the tension has to be 120 newtons. Same over here, tension. Okay, so what's going on here? We have two masses pulling on the string. Both of them are pulling with 120 newtons, so shouldn't the tension be twice as big? Well, no. Because in part A and part B, there was actually two things pulling with 120 newtons as well. It's the same in all three of them. In the first problem, it was the ceiling that was pulling on the string with 120 newtons. And in the second one, it was the wall pulling on it with 120 newtons. In the third one, it's one of the other masses. But in all three cases, the forces are all balanced. Okay? So even though in the third case it's some mass that's providing this balancing force that's pulling the string down, in the first two problems the mass was balanced as well by other normal forces in this case. So we've got a normal force that's balancing it out, normal force that's balancing it out from the wall and from the ceiling. Okay, page 2. We have here 3 sleds tied together and pulled east across an icy surface with an applied force of 12 newtons east. The mass of sled 1 is 12 kilograms. I'll write that in here, 12.0 kilograms. The mass of sled 2 is 11.0 kilograms. And the mass of sled 3 is 7.0 kilograms. We're assuming there's no friction. Cool. We want to determine the acceleration of the sleds. This is where we get to ignore friction. I am always happy when we can do that. So we want to find the acceleration of the sleds. We're told here that we have 120 newtons. And actually, just notice here, this said 12 up in the top in the question. It's 120. That was a typo. Okay, so we have 120 newtons. I can draw this whole combined sleds, all 3. Right, we've got a free body diagram for those. And we have the forces. We have normal force, gravity, and we have our one applied force, which is 120 newtons east. That's everything that's going on. Now, this is all 3 sleds. This is what's happening to the 3 sleds when we put them all together. And their mass, it's equal to 12 plus 11 plus 7, which is equal to 30 kilograms. Perfect. So then we can just use our second law. F net equals ma, which means that our net force, 120 newtons, is equal to our mass, 30 kilograms, times our acceleration. And we can solve for the acceleration, 120 over 30, so 4.0 meters per second squared. There you go. You see, we didn't have to look at tension at all for that problem. But now we want to take that information and find out then what the tension in rope A and the tension in rope B must be. So let's find out. Now this box wasn't supposed to be this small. I'm sorry about that. But rope A, let's look at rope A here. Well, rope A is pulling sled 3. So let's just look at sled 3 all by itself here. So sled 3. What's happening? Well, we can say that the net force is equal to ma. Okay. We know that the net force here is just the tension in rope A, so FTA. That's how I'll write that, the tension in rope A, FTA. And that's equal to its mass, 7 kilograms, times its acceleration. And we know that the acceleration is 4 meters per second squared. So then we can do 7 times 4. We can say the tension in rope A is equal to 7 times 4, which is 28 newtons. And we're done. Now we want the magnitude of the tension in rope B. Looking back at rope B here, rope B is pulling two sleds. It's pulling sled 2 and sled 3. Right? And that's important to realize, that rope B isn't just pulling sled 2. It's the one rope that's pulling everything behind it. So it's pulling sled 2 and it's pulling sled 3. So to solve this one, I'm going to look at sleds 2 and 3. And I'm going to draw a free body diagram for them. So this is 2 and 3. Again, they have their normal, gravity, and they have the tension in rope B. That's the only thing that's pulling them this way. There's no friction. So we have the normal and gravity. Okay, so once again we can say F net equals MA. Here our net force is FTB. And that's going to be equal to our mass. Well, we need to calculate our mass. The mass here for sleds 2 and 3, that's equal to 7 plus 11, which is equal to 18 kilograms. Okay, so 18 times, again our acceleration is 4 meters per second squared, and that gives us a tension then of, 72 newtons. And there we go. That was our tension in rope B. That's all we needed to do. Now, we could have looked at it a different way. Oops. We could have looked at this a different way, where we could have looked at sled 1. We could have drawn sled 1 and said it has 120 newtons acting this way. It's got the usual normal and gravity. And it has the tension of B. And then we could have said that it has a mass of 12 kilograms. Oop, and 1 second, I just lost my my pen. There we go. Has a mass of 12 kilograms, an acceleration of 4, and we could have said the net force in this case is 120 newtons to the right minus tension in B to the left. And then we would set that equal to MA and solve that way. Now, we don't need to do this. We don't need to solve this way because we already solved it once. We already found the answer. I'm just showing you that there's a second way that we could have looked at this problem. Okay, final page. Kinematics and Newton's laws. So we want to bring in now our kinematics equations from Unit 1 and use those to look at these sorts of problems. Now you might remember from kinematics equations, they all assume constant acceleration. Right? We had equations that had initial velocity and final velocity and those sorts of things, but no initial acceleration and final acceleration. We just have one value for acceleration. It's constant through the whole problem. So when A is changing, right, if we have starting off at, let's say 10 meters per second squared, and then it goes to 0, and then it goes to 10 again, something like that, we need to break it into separate pieces. So we need to break the problem into steps, so that each step has a constant acceleration. So that's what we're going to look at in this last problem here. The problem says, starting from rest, an ice skater pushes the boards with a force of 130 newtons and moves that distance. He then moves at a constant velocity before he digs in his skates and starts to slow down. When he digs in his skates, he causes a net force of 38 newtons to slow him down until he stops. Okay, so we've got 3 steps here. We've got step 1. We've got step 2 where he's moving at a constant velocity. I'll put that in here. And we've got step 3 where he slows down. So step 1 he's accelerating, step 2 he's going at a constant speed, step 3 he's slowing down. So part A says determine his acceleration when he is pushing on the boards. So we can say here he's pushing on the boards, and here we're using Newton's third law again because he's pushing on the boards west, which means that the boards are pushing him east. So this is the skater. So even though it said 130 newtons west, the force that he experiences is to the east. That's the reaction force that he is experiencing. Okay, so we're going to work with that. We're going to say that, again, F net equals ma. We know that his net force is this reaction force here, so we've got 130 newtons east. That's equal to his mass, which was 54 kilograms, times his acceleration. So then we can solve acceleration equals 130 over 54. And that gives us, in 1 second, gives us 2.407. There's his acceleration. Okay, now we want to find out what's his acceleration just after he stops pushing. Remember, this is step 2 where he's moving at a constant velocity. Well, constant velocity means there's no acceleration, which means that a is equal to 0. Done. And when he starts to slow down, well, we're told that he digs in his skates, causing a net force of 38 newtons west. So, F net equals ma. Always a good place to start. We know that the net force here is 38 newtons west, and that equals his mass, 54, times his acceleration. So a is equal to 54 over 38, which is equal to 0.704 meters per second squared in the west direction. Beautiful. So, how far does he move? Ooh, this is a bit tricky. Because again, we need to do this in 3 steps. Step 1, step 2, and step 3. How far does he move? Well, to do that, we need to actually find out a couple pieces of information. In step 1, we're told how far he moves, 0.704. So for step 1, I can say delta D equals 0.704 meters. But I'm not done with step 1, because I need to use its information to find out how fast he's going in step 2. Because in step 2, we're just told he's going at a constant velocity for 4 seconds, but we don't know what the velocity is. So I need to find what the final velocity is for step 1. Hopefully that makes sense. So step 1, we need to find the final velocity. Vf equals question mark. So we're going to use the delta D. We're going to use also the acceleration. We know that his acceleration there was 2.407. That's what we calculated. And we know that the initial velocity was equal to 0. He started at rest. So we'll use all of that information to find Vf. Use one of our equations. Vf squared equals Vi squared plus 2a delta D to find Vf. Vf is the square root of Vi squared plus 2a delta D, which means it's the square root of, well, Vi was 0, so that's nice. 2 times 2.407 times delta D, which was 0.704. And that gives us, for Vf, 1.841 meters per second. Good. Now we needed that for step 2. Step 2, we're told that he's going at a constant speed for 4 seconds. And now we know that his constant speed was 1.841 meters per second. We have the equation delta D equals V delta T. So we've got 1.841 times 4, which gives us 7.364. Perfect. Last step. Well, then we need to put it together. But step 3. We know now that his initial velocity is this same speed here. Vi is equal to 1.841 meters per second. He's slowing down to a stop, so his Vf is equal to 0. We know that his acceleration, we calculated that above, it was to the west, so I'm going to say it's negative. Negative 0.704. And we want to find delta D. We'll use the same equation as before. So we'll use Vf squared equals Vi squared plus 2a delta D. Now we need to solve for delta D this time. Vf squared minus Vi squared over 2a. Now Vf was 0, minus Vi was 1.841 squared, over 2 times our acceleration was negative 0.704. And putting that all in, it gives us a value of 1.981. Perfect. Now we just need to get our total. And say delta D is equal to, and we grab our delta D's from each of the steps. So step 1, we had 0.704 plus 7.364 plus 1.981, and that gives us a grand total of 10.1 meters. Great. Thank you guys. I know this is a long one. Great. Have a good one.